All right, hello everyone, my name is Addison. Today we are doing the weekly review for Math 2413. AKA differential calculus. All right. So how is everyone feeling right now? You can go ahead and feel free to use the chat or use your mic. All right, so I understand that right now you guys have done a Chapter 1 review as well as the tangent and velocity problems in Chapter 2, correct? All right. All right, so let's go ahead and get started. We're going to go ahead and do a quick Chapter 1 review. All right, so let's go ahead and just start with section 1.1. I'm going to try to move a little fast on chapter 1 since most of this is kind of review, but if you ever need me to stop and slow down and elaborate, just let me know. All right, so let's go ahead and get started. So the first thing we need to do, section 1.1 is going to be 4 ways to represent a function. So what's the definition of a function? Well, a function is going to be a rule that assigns to each element so we have each element x in a set D. What sections? We're going to go over, I'll do a quick dive over all of chapter 1 and then section 2.1. Is that where you're at, correct? All right. And then in each that we have, that will produce exactly one element. Called f of x in a set E. So essentially, just to break this down, something that's a little bit easier to understand, we know that our x value is going to be part of a set D called the domain. And that's going to be the range of all x values. And then our y is going to be a part of set E, which is also called the range. So that's a quick little review for that. And then we also know that our domain is going to be our independent variable. And then our y is going to be our dependent. All right. So now that we have that out of the way, let's go and discuss the 4 ways we can go ahead and do a question. So now we have verbal. We have numerically. We have visually. And lastly, we have algebraically. So verbal just means we're going to go ahead, it's what it sounds like, we're going to go ahead and just use word, like a set of like phrase or words. Numerically means that we're going to actually use a set of values or a table. Visually means we're going to use like some sort of visual such as a graph. And then algebraically means we're going to use some sort of explicit formula. So for like a quick example of this, let's go ahead and use just so how each of these will work together. So let's say we have a problem and we know that one pencil costs 10 cents. that would be an example of a verbal. Now for numerically, we can make a table. So let's go ahead and say number of pencils and then cents. Then we just have 1, 10, 2, 20, 3, 30. That's going to be an example of numerical. Then we have visually, so we know, we can go ahead and create a graph. So let's say we have our cost in cents, and then we have our number of pencils. And then it would just look something like this. And then we can just go ahead and assign each number to one particular Y. And that would go ahead and be a visual. And then lastly, for algebraic, we can go ahead and say that our f of x is going to equal 5x, which you can equal y. And that would just be an algebraic. So now that we have that, we can also just go ahead and do a quick review of our other types. We can do of functions. We have a piecewise, which is going to be, it's just going to be a set of multiple functions all put together. So an example of this would be, we can have our f of x is created by a set of some g of x, some h of x, and however many we need, and then each of these will have some specific domain. So let's say in this example, our g of x, our domain is going to be for all x's greater than 0, but then we need to define the rest of it. So let's say this could be for all x's less than or equal to 0. So that would just be a quick review of piecewise, just putting different pieces together. And it's also important to note to check whether or not we have a less than or equal sign, right? Like an equal sign or not, because that can affect the way our graph can actually be set up, especially when you start hitting limits. That can really affect how things move. And then now let's go over our even and odd functions. So our even function is going to be defined as, it's going to be any function to where our f of x, or negative f of x is going to be equal to f of negative x. Or in better words, essentially just think of it as being mirrored across our x-axis, right? Y-axis, y-axis. Sort of like this. We can see that's a perfect mirror across each axis. And then now we can go ahead and define our odd functions. And then that is going to be whenever we have our f of negative x is going to be equal to negative f of x. So essentially it's going to look something like this. So where we can go ahead and then essentially if you look closely, we kind of have some mirror against the y equals x. So that just essentially is a quick thing to determine even or odd. And then last thing we need to go over for section 1 is going to be increasing versus decreasing. So we know that a function is going to be increasing. If and only if we have some value, let's say we have our x1 and x2, where x2 is greater than x1, then our f of x2 has to be greater than our f of x1. And then f of x is decreasing if and only if we have some x2 that's greater than x1, and then our f of x2 is less than our f of x1. So that should be about it for section 1.1. Is there anything you want me to do a quick example over, anything you need to go over real quick before we move on to section 1.2? All right, I'm going to go ahead and move on to section 1.2, which the basics are going to be math modeling and then our different types of functions. So the basics for math modeling, essentially, let's say we have math modeling is just a way for us to kind of determine how to solve a problem. This is just a sort of like a way a method to find a solution. So let's say we have some sort of real world problem. Well, then we need to figure out a way how to figure out how to solve it. So we can go ahead and think about what we can do. So then that leads us to where we can actually create some sort of model, whether it's a graph, an equation, whatever. And then we just kind of use that and just kind of formulate and solve for it. And then from that model, we can actually go ahead and look and see how it works. And from that, we can go ahead and create some sort of conclusion from that model. And then from that conclusion, we can go ahead and interpret results. And then interpret our results and see if they apply. And then let's see if that can have a real life solution. However, it's always important when we do this to go ahead and test out this whole idea. Because if this is wrong, because if that real world solution does not work, then we're going to have to go ahead and go back and test it out, and then go ahead and restart this whole cycle over again until we have something that works. Now that we have that, let's go ahead and go over our different types of functions real quick. All right. So now let's go over our basic ones. So our basic ones, we're going to have our linear function. And this is going to always be in the term f of x equals y equals mx plus b. And it's important to note that's not going to be any sort of exponent over the x. It's essentially saying we have x to the first power, therefore it's always going to be linear as long as our highest power for x is going to be 1. Then we can actually move on to higher and higher powers, such as quadratics, which are going to be f of x equals y equals ax squared plus bx plus c, and they're defined by having that x squared right up here. And then we can move on to cubic and so on and so forth. It's just essentially these powers are always going to get bigger. And now that moves us on to general polynomials. And they are essentially just defined as having some equation, we can call it f of x, equals some coefficient a times x to the nth power plus b times x to the n minus 1 plus c x to the n minus 2, and so on and so forth until we get, let's say, some number d times x to the 0. Now, it's important to any of these coefficients can be 0. Like, we don't have to have them in there. They can be 0, they can be whatever we want as long as it's some real number. And it's also important to note that this n also has to be a positive number, bigger, at least 1. So n has to be greater than or equal to 1 for it to technically be considered a polynomial. However, that's something we can go ahead and we'll look at more later. And then essentially most polynomials will have a domain negative infinity to infinity. Not all, but most will. We can go, once again, as we move into more function types, we'll see where there's differences between that. All right. And then we have our power functions. And they are defined as having some f of x, which equals x to the a, and then a must be a constant. So for example, that would be, let's say, f of x equals x to the 1.5. That a is always going to be constant, but we can go ahead and change on whether or not we want to plug in 1, so we can have like 1 to the 1.5, 2 to the 1.5, so on and so forth. Then, however, we also need to be careful not to confuse these with our exponential functions, because exponential functions, on the other hand, while they're similar, they're a little different. Exponential are going to be defined as having f of x equals some constant a to the x power. So a is still constant. However, that x is the thing that changed. So let's say we have f of x equals 2 to the x, then we can go ahead and plug in 2 to the 0, 2 to the 1, 2 to the 2, but those are all going to be different powers of 2. So those are a big thing to keep an eye out and not get those confused. And then we just have some other quick ones. We have our trig functions. Those are going to be using some sort of trig identity. And then those would be things such as sine, cosine, tangent, and all of those, and all of their derivatives. We're gonna have our root functions. And then those are going to go ahead and be defined as f of x equals x to the 1 over a. Or essentially that means they can be written that's another way of essentially saying x to the a root. Now we have our rational function, and then lastly we have our rational functions. And that's essentially saying we have some function f of x that is created by dividing two other functions. So let's say we have g of x and h of x. However, h of x can never equal 0 for this to fully be like a true function, to have like no gaps in the domain or anything. So h of x can never equal 0 in these. All right, and then our last function is going to be, let's see if I can squeeze it in real quick, our log function. And then that's going to go ahead and be defined as f of x equals log to some base a of x. All right, that should be it for different types of functions. Okay, so transformations, our main types we're going to have are going to be translations, which is sliding. And we can essentially slide things up and down or left and right. So if we want to go ahead and move things up or down, we can go ahead and change it as saying, let's say we have our original function of x. Well, we can, so let's go ahead and say original f of x. And now to slide it up and down, we can go ahead and say we have our f of x, our y equals f of x plus or minus c. If we add c, it goes up. If we subtract, it goes down. And then we can also slide it left and right. It's whenever we have our, so if we have our y equals f of x plus c, that means we're going to go ahead and slide it c units right. I mean left. And then whenever we have our y equals f of x minus c, we're going to go ahead and slide it right. And that sounds kind of counterintuitive, but when you actually plug numbers in, it makes a little bit more sense as to why they slide those certain directions. And next we have our stretching. So stretching essentially just changes like what the height to width ratio is. So whenever we stretch something, we're going to go ahead and let's say we have our original one like this. Stretching means we're going to change it to something like this, where we have the same domain, but the height changes. And if we shrink it, it's going to be a similar thing, but we see how the height is going to go ahead and decrease. We can do this either horizontally or vertically. If we want to go ahead, so for our vertical transformations, we can go ahead and either stretch it by having sum y equals c times f of x. And then that's going to go ahead and stretch it. Or we can divide by c. That's going to go ahead and shrink. And then for horizontally, we can go ahead and say that we have sum y equals f of x over c, and then that's going to actually stretch it. And then to shrink it, we could say we have sum y equals f of c times x, and that's going to shrink. Yeah, when it comes to a horizontal change, like I said, they kind of seem counterintuitive. When you actually plug numbers in, they begin to make a lot more sense. And then our last ones are going to be combining. Okay, give me just 1 second to plug in my laptop. All right. All right, and lastly, we have our combinations. So we can either add and subtract functions. So this is assuming we have some function, two functions, f of x and g of x. We can go ahead and add functions. So we can say we have f of x plus or minus g of x. We can also say that means f plus or minus g of x. That's just essentially a different way of writing it. So we can essentially add or subtract functions however we want. Now we can do the same thing with multiplying and dividing. We can say that we have f times g of x equals f of x times g of x. We can divide similarly. We can say we have f over g of x equals f of x over g of x. And the last thing that's going to be most important is going to be our composite functions. So our composite functions are essentially when we're going to put one function inside of another. So let's say we have some function that's going to be f of g of x. And this can also be written as f little circle g of x. What this is essentially saying is we are going to go ahead and let's say we have some sort of g of x. We can either do it as just a regular formula, or we can actually put a constant in to solve for it. So let's say we're going to get x equals 1. We would have to solve for g of 1 first. And then once we have that value, let's say g of 1 equals 2, then we'd plug that 2 value in, and we'd have like our f of 2. That's essentially what it's saying. It's like you're solving for some sort of g of x, and then whatever values you have in for x for your original function, that's where you're going to plug in that value of g of x into. All right, we're going to go ahead and, so everyone doing okay so far? Does anyone want me to do any examples of anything? All right, so now we're going to go ahead and move on to our exponential functions. All right, so there's actually some good uses for exponential functions. So a really good use for them is going to actually be, one way we could use them is we can actually go ahead and use them for approximation. So let's say that we have some number that's going to be really hard to solve for, or let's say we're having to mess with some irrational numbers. Those are not fun to mess with. So let's say we're having to find some value. Let's say we're trying to find some value. Let's say they're wanting us to find what 2 to the e is. Well, that's not going to be really fun, because essentially that's just like saying we're wanting like 2 to the 2.72, so on and so forth. Well, what we can actually do is we can go ahead and approximate using our exponential functions. So let's say we have some function 2 to the x that we're using. Well, say we have our graph that looks like this, and then we have 2 to the e right here. Well, we could actually use this to go ahead and guess and find an estimate using stuff that would be a little bit easier to say. So let's say we have 2.7 right here and 2.8 right here. So when it makes sense to say that we have that in between here, we can find some estimation. So essentially what we can say is, since we know that 2.7 is less than e, which is less than 2.8, then we know that 2 to the 2.7 which is going to be less than 2 to the e, which is less than 2 to the 2.8. Now, 2.7 and 2.8 still aren't really fun powers to mess with, but they're definitely a lot, if worse comes to worse, that's a lot easier to mess with than saying e. And we could expand this out more if we wanted to find a more general estimate, so we could say 2 to the 2, 2 to, as less than 2 to the e, which is less than 2 to the third. So we know that this 2 to the e is essentially going to be somewhere in between 4 and 8. So that's a good use. And just a good way to recognize your exponential functions, just to make things clean. So there's essentially 3 ways our exponential functions can look. We can have them look like this. To where they're going to start small and then get a lot bigger. And whenever we have that actually signifies that we have some function. You have some function, let's say y equals b to x. Well, we know that b is going to be greater than 1, since this is going to be increasing. Since this is increasing. We can also have something to where it stays the same. So now we have, so this would actually, since this, let's say this is at y equals 1, we can say that y equals 1 to the x, because essentially b has to equal 1 if that's, because 1 to any power is 1. And then lastly, real quick, we're decreasing. That means we have our y equals b to the x. And then b is going to be in between 0 and 1. And then next thing we need to go over is our exponent rules, which is going to make life so much easier, especially as you go through calculus. These are really good, important things to know. So if we ever need to break down really big exponents, we have several rules to help us. We can say that b to the x plus y equals b to the x times b to the y. B to the x minus y equals b to the x over b to the y. B to the x all to the y power equals b to the xy. And then lastly, a times b to the x equals a to the x times b to the x. So these are all really, really important. You're going to have to make sure you keep these in mind, especially, like I said, especially as you start going through and you start doing more and more complicated derivatives. It makes things it really helps to break down different pieces. And then just the last thing we need to keep in mind is our natural exponent. Our natural exponential function is just going to be y equals e to the x. All right. All right, and now we're on to our last section of chapter 1. So which is just going to be our inverse and logarithmic functions. So first thing we need to do whenever we're dealing with inverse functions is define what one-to-one functions are. So a one-to-one function that is going to be defined as essentially saying that every x is going to have a y, it's going to have one y, and every y is unique. So now that we have this, defined, it's essentially saying, does this pass the horizontal line test? So the horizontal line test, that essentially means we draw a horizontal line, does it touch more than one y? If it does, then it's not one-to-one. If it does not touch more than once, then it is one-to-one. So now we can go ahead and move on to actual inverse functions. So an inverse function is essentially saying, like, a way to think of it is how can we go ahead and manipulate the function so we get like an opposite function almost. So like a good way to think of it is cancellation. So when it comes to cancellation, that's essentially saying if we plug our original function into the inverse, do we essentially get our initial values back and vice versa? So let's say we have our function f of x, and then we have our inverse function f inverse x, and essentially just what it's saying, let's say we plug in any x. So we can have our inverse function, and then we can go ahead and do a composite function, plug in our original function in. Well, we need to be seeing x come out of this original function because this is what we put in, and then this is what we're putting back out. And we can do the same thing in reverse to where we can go ahead and plug in, where we have our inverse plugged into our initial, and once again see the same thing come out. And then, so how to solve for our inverse functions? So the first thing that we're actually going to do is we're going to go ahead and just establish that we have some function, that our function f of x is going to equal some y equals some sort of y. Just go ahead and just for this example say that we have a linear function. So a linear is going to be y equals mx plus b. But once again, this is just solely for example. All right, and then the next thing we're going to do is we are actually going to go ahead and essentially find some function to where we can go ahead and solve for our x, and then solve for x. So where essentially our new value looks like x equals f of y. So where we just have x by itself, you can't always do that, but it's a good way to try. If that doesn't work, if you can't just find it easily on its own, then you're going to go ahead and have to go ahead and switch everything initially and then try to solve for it again. But yeah, that just depends on the type of problem. And then the last thing you're going to go ahead and do is just switch your x and y variables. So essentially we're taking this and just saying that our y equals f of x. or well, let me better put it where we have x equals g of y, so we don't get confused with the original. So now we are writing y equals g of x. Like I said, you may have to swap 2 and 3 if you can't necessarily solve for x in the initial, swap steps 2 and 3, and then you should be able to find it that way. So, and then now our next type of special inverse function is going to be our log function. So our log function, let's our log function with our base b. This is going to be the inverse of an exponential. And essentially what this is saying, let's say we have some log with our base b to the of x equals y. And that's essentially like we're saying that this is essentially the inverse of saying b to the y equals x. This is just a so that's just a way how to say that, or as my pre-cal teacher liked to say, the base to the base to the power across the equal sign is the quantity next to the log. So that's just a good way how to go back and forth between exponents and logarithmic, just because it's kind of hard. Like you may have a situation where like you may have y, but you need x, or vice versa. That's just a way how to go back and forth. And then lastly, we have our natural log. Also noted as ln, which is essentially saying we're having our log base e. And then one last note with inverse trig, if you're taking the inverse of a trig function, you have to limit your domain, because that's when things are going to get really squirrely and it's not going to be a true function on the other side. So you have to go ahead and limit your domain. All right, now we can get to more fun math, which is our tangent and velocity. So first I need to go ahead and define our tangent, what a tangent line is. So our tangent line is going to be the line which intersects with some function at, let's some point b, or some point x naught, only at x naught. So essentially what it's saying is we have some function, look, let's say we have this quadratic function, and essentially it's saying that our tangent line, and then this is our point P, or our x naught, and then this is essentially saying our tangent line is only touching this function at that x naught. So now let's look into how we can actually go ahead and solve for our tangent line of any specific point. All right, so let's say we have our function f of x, and let's say it moves around a lot. Let's say it looks like this. So if we actually go ahead and pick our point x naught and draw our tangent line like this, if we look really, really close, so let's go ahead and attempt to try to zoom in on this. If we look really close, we can see that this point right here, anywhere on this curve is going to have some sort of slope at some sort of point. Well, your tangent line slope is going to be the slope, like the instantaneous slope at that point. So our tangent line slope is going to be our tangent line of x naught, our instantaneous tangent slope at x naught. So now how do we go ahead and find this? Because right now there's not really a good way. We don't really have many points of reference, do we? So we can go ahead and we can actually use a good estimate. So let's say once again we have our tangent line, we have our curve, and our tangent line. Well, we know our tangent line is going to look something like this, but we don't really have a good way of approximating it, do we? So what we can do is we can actually use what is called our secant line. So a secant line is going to be a line it's going to be a line that connects, that touches the function at exactly 2 points. So what we can do is we can make a secant line using that original point and put it anywhere we want to, but however, let's go ahead and use several different spots. So let's say we want to put one right here, one right here, and one right here, using these different values of x. So let's go ahead and draw all of our lines so we can see from right here. That doesn't look very close to our tangent line, but we can move closer. That orange one looks a lot closer to the green one. So we can move even closer. So so essentially what we have to do is we have to find as close as an approximation as we can. But essentially the closer we get, the more accurate our approximation is going to get. So, but we can still go ahead and use our secant line. So our formula for finding it is going to be essentially our normal slope formula. So let's say we have, let me go ahead and draw a cleaner picture right here. let's say that we have our point. Our point right here is going to be x naught, y naught. And then we're going to have our point of approximation. So let's say we have this right, we're going to use this point right here, for example, and we're going to call this, and this is just going to be s and f of x. Well, we can just go ahead and use our basic slope formula in order to solve for the m of that secant line, which is going to be our approximation. So we can go ahead and say that the slope of our secant line is going to be our f of x minus y naught and our x minus x naught, and then x and f of x can be any point you want. So let's say our f of x, our x and f of x, let's say this point right here is going to be 1, 2. Then essentially we would go ahead and plug in 2 minus y naught over 1 minus x naught. That's essentially what it's saying. So now that we have that out of the way, let's go ahead and try a sample problem. So let's say we have some function let's say we have x squared plus 1. And then we want the tangent line, and then we want to find the equation for the tangent line. At 0.25. So let's go ahead and see. So what would be maybe a good point to try in order to solve for our slope? So like if you want to use the chat or to speak up, like what's a good point you want to try? Or like an x value. 7. All right, we could try 7. That would be kind of far off, but we can do it for x equals 7. So now let's try our secant line at x equals 7. So this is going to be a pretty bad approximation, but we can just go ahead and show how you could go ahead and use this tactic. So we know that f of 7 is going, so we know that f of 7 is going to be 50. Yeah, that's going to be pretty far off, but once again, it's just showing basics of how to do it. So now we know that we have our, so now we have something like this. That's going way, way up there. So now we have our secant line. So now we have our 2 points. We have our 2, 5, and then our 750. So what we're going to do is we're going to do our change in y. So we're going to have 50 minus 5 over 7 minus 2. And then that's going to go ahead and get us 45 over 5. So therefore, the slope of our tangent line would be 9, or our approximation. So what we can go ahead and do is we can go ahead and use our point slope form, knowing that we have our original spot right here. So we know that our point slope form is going to be y minus y naught equals m times x minus x naught. So we can just plug in our values that we know. So we have y minus 5 equals m times times 9 times x minus 2. We can get y minus 5 equals 9x minus 18. And then we're left with y equals 9x minus 13 as our approximation of our tangent line. However, if we want a closer approximation, let's say we'd used 2.5. So now we have f of x still equals x squared plus 1, and we want tangent line at 2.5, and then we're going to go ahead and use our approximation at 2.5. So that one's going to be a little less fun to mess with, but we're going to have 2.5. 2.5 squared is going to be 6.25 plus 1, which is going to be 7.25. So actually we're just going to go ahead and get 7.25 minus 5 over 2.5 minus 2, which is going to be 2.25 over 0.5, which is going to be 2.5. Well, we can see this is going to be much, much lower. So we can just plug things back into our original, back into our point slope. So now we have y minus 5 equals 2.5 times x minus 2. So now we can go ahead and plug in, and so now we're left with y minus 5 equals 2.5x minus 5, y equals 2.5x. So we see the slopes on those were very, very different, so it's important to try to find one that's a very close match. So now let's go ahead and try limits to actually go ahead and see how we can get a different effect. See if there's a way we can see if that's a good approximation. So let's say we know that our m is 2.5, right? Our m is going to be 2.5. All right, so I know they haven't necessarily introduced limits, but here's a good way to kind of test. So essentially, we're going to go ahead and use the same thing, but we're going to take our limit. So what we're going to do with our limit, so we know that we have our f of x minus y naught over x minus x naught. So now let's go ahead, and when we take a limit, that's essentially saying we're getting infinitely close to that number as possible. So now what we're going to have to do is we're going to go ahead and get very, very close. So what we're going to say is we're going to take the limit as x approaches 2. Since that's essentially saying we're getting as infinitely close to 2 as we possibly can of this value. So now we know that our f of x, any f of x is going to be x squared, or x naught. So we have x squared plus 1 minus 5 over x minus 2. That's just over, x minus 2. So now let's go ahead and plug this in, and we end up getting x squared minus 4 over x minus 2. Well, we can go ahead and factor this out and go ahead and just take our approximation to where we get x plus 2, x minus 2 over x minus 2. So we have our limit so now we get 4 for our limit. So we can see 4 is, so then we have that limit, we plug our 2 back in here, so then we get 4 as our m. we can see that's a lot closer than that's going to be closer than what we had earlier. So that's a good way to do it. However, like I said, we'll go over limits more next week. And then last thing I want to touch on real quick before we go is our velocity problem. And essentially just the way you're going to solve velocity is going to be a very similar way. So let's say we have so it's important to know that there's a difference between average velocity and instantaneous velocity. So we know that our average velocity is going to equal essentially our change in position. So let's say we're going to call our position P over our change in time. Well, that kind of gives you just a general idea. So let's say we have a graph of position and time. Well, we can go ahead and find an approximation of speed at a certain point by once again doing our secant line. But it's also important to note that at each point, whenever you're moving along a curve, you have an instantaneous velocity. In order to find our instantaneous velocity, we are going to have to do, we're going to end up having to actually find the tangent line at that position. So once again, that would just be finding the tangent line right here, and then just finding the slope, and that's going to be your instantaneous velocity. So does anyone have any examples or have anything you want me to go over, like for anything we've covered today? All right, so let me go ahead and just do, another tangent problem. So let's say we have, a function that is going to be tangent slope. So yes, once you get the tangent slope, that's the tangent slope of that. If you have a position versus time graph, the tangent line at that point you're looking at is the instantaneous velocities. So yes, so it's essentially saying that m equals instantaneous velocity. Does that make sense? All right. So yeah, let's go ahead and do one more question. Yeah, so let me go ahead and just think of a question. Does anyone want to give me just an equation? We can work through it. Just any equation in a point. Or are there any other quick topics that you want me to brush up on that maybe you learned like yesterday or something? All right, if not, then I'll just go ahead and move forward with doing just another, I'll go ahead and do a velocity problem. So let's say we have our position versus time graph. So let's say it's going to look something like this. So we have our position and our time, and let's say it just looks like this. So now let's say we want to find the average velocity And then actually I'm going to go ahead and just say this just a all right, average velocity from points from t is in between 0 and 2, and then our instantaneous at t equals 1. And then let's say it is defined as p equals t cubed. So yeah, now we have our p. So now we know that p equals t cubed. And then we are looking, so now let's go ahead and start with our average velocity. So at t equals, so p of t, p of 0, given p of t, is going to be 0, and p of 2 is going to be 8. So once again, this is just saying that we're finding our change in position over change in time. So our position goes from 8 to 0. So we have 8 minus 0, and then our time goes from 0 to 2. So 2 minus 0 equals 4. So that is going to be our average velocity. Is going to be 4. So now we're going to look at our instantaneous velocity at t equals 1. So let's go ahead and say we want to approximate using 1.1 as our approximation. So now we have our point 1, 1, and then our approximation point is going to be 1.1, and then that is going to be 1.331. So now we're just going to find our approximation for our secant line, and that is going to be, so then we're going to find our approximation for our secant line, which is very similar. So we're going to do 1.331 minus 1 over 1.1 minus 1. So now we're left with 0.331 over 0.1, and that's essentially saying multiply times 10. So now we are left with 3.31 as our instantaneous velocity. Yeah, so for velocity problems, you're typically not going to have to plug anything back in, since they're usually not going to ask you for, like, well, what is going to be the exact line? Like, if they gave you like a normal problem, it's a normal algebraic problem, then they would probably ask for a line. But if they're asking for velocity, they're probably not going to tell you to plug anything back in. So you can typically just stop once you have your instantaneous velocity. And just a quick note, these actually aren't that far apart. So sometimes, like, you can use your average as for the points around it as the guideline, but once again, that shouldn't be like completely like this is gospel, this is what it is. There will be some differences. So yeah, so does anyone have any last second questions before I end the session? All right, sorry if things are kind of boring or if things didn't really go well. This is my very, very review session, but thank you all for taking the time to come out, and good luck on your homework and for the rest of the week. Yeah, hopefully next week will be a little more interesting, because that's when we start getting into more that's like more things that are maybe actually new rather than just like pure review. And then recordings should be available on e-learning.